All right, let's go. Till 47 of 9. 947, okay. All right. Bro. Well, all right. I guess I have to manually enable Pro Search now. Noted. There we go. Yo, yo, yo. I'm gonna have it update that just so it's that way it's not doing pointer shit that I have no idea about. Damn, I feel like it's able to generate significantly more content than before. I could be wrong though. Holy shit, dude. Okay. Okay. Excuse me. All right. Work on being as accurate as possible without giving irrelevant information. Let me get a pillow. Okay. I haven't seen what R values are actually called. If an L value is a left value, I figure an R value is a right value. But R values refer to unidentified values that must be used immediately in their expression. L values evaluate to named identified objects, or we can say that R whereas R values are so when we assign an R value to an L value, or when I assign so the assignment operator expects a modifiable L value on its left operand, which is why we can't assign an L value to an R value, but we can assign an L value to an L value because the L value on the right can be converted to an R value. Okay. Okay. Compound data, a compound data type is a data type that is defined using fundamental data types. Function signatures include multiple fundamental data types. Well, I guess you could have a void do thing void, but another example. We have references, we have pointers, we have classes, which are classes, structs, or unions. C style strings. Okay. Can a const expression function call a non-const expression function? A const expression function can call a non-const expression function when the const expression function is not being used in a compile time context where it must be used at compile time. This is because the non-const expression function doesn't, because there's no guarantee that the non-const expression function will be, at compile time. So using the const expression function, which must be evaluated. Is there a way of making this? A const expression function can call a non-const expression function only when itself is not being used in a context that requires compile time evaluation. When it is not being used in a context that requires compile time evaluation, because there's no guarantee that the non-const expression function will evaluate at compile time, which prevents the const expression function from evaluating at compile time, since functions that it calls must execute at compile, or must be evaluated at compile time. We use const eval instead of const expression functions. Const eval immediate functions instead of const expression functions when we want the function to guaranteed evaluate at compile time. When we need the function to guaranteed execute at compile time, since const expression functions can also evaluate at runtime if not used in a context that requires compile time evaluation. Const expression, I think that's the main difference. Const expression functions may be evaluated at compile time if used in a context that requires it. Const eval functions always evaluate at compile time, forcing their parameters to also be const expression. I'll see val functions always evaluate at compile time, forcing arguments in their calls to be const expression. Some haunted shit. What the hell? A const expression function is a function that evaluates at compile time if its restriction is satisfied. Its restriction is that it is used in a context that requires, that requires a const expression. Which forces it to evaluate at compile time. Not thinking about the parameters. It's not limitations. What are its restrictions? A restriction for a const expression function. Okay. The restrictions of a const expression function. Seems like it's a use case. Because you put it there to be evaluated at compile time. So that the compiler will optimize it. Or just run it at compile time, which even if it doesn't do any optimization, it's more efficient than having to run it at runtime. Compiling shaders, for example. Oh, what did I eat, man? I fucked my stomach up. And I had a salad. That was pretty recent. That must be what it was. Damn. I did drink milk with the salad. That was probably dumb. And I didn't drink the milk first. So I did not follow the add acid rule. Wait, who was that? Okay. Function templates in multiple files. Not const. If I'm thinking const expression functions still. For template functions. Was it similar? Where the linker wasn't happy? I think it needed to be in the same translation unit. I could be wrong though. Let's try. Oh yeah. Let's get a timer going. Let's see how long I've been going first. So an hour and 8 more minutes. So excuse me. This forward declaration is okay. Yep. Well, yeah, so it doesn't like it. What happens if I make it inline? Same thing. It's being called twice. We have a definition. And the linker won't move it, so okay. I think it said that const expression functions are implicitly inline, but not templates, but I thought they functioned the same, maybe not though. What if we make it inline? No, what if we have another? Okay. Oh wait, oops. Okay. Okay. To use function templates across files, it is recommended define function templates in a header file to include them in any file needing their functionality. Functionality. The linker will not link definitions with forward declarations and calls in different translation units. So header files let us conveniently include the definition in each translation unit. Forward declarations would work only when the definition is in the same translation unit as the forward declaration unit. Excuse me, non-type template parameters are template parameters of a given, not placeholder, type that require a const expression value. Calls to the function template can pass the non-type template parameter via angled brackets. Example. Template int x void do thing. We can call do thing and pass it a const expression int via doThing Okay. Non-type template parameters are template parameters of a given type that require a const expression value, that require initialization with a const expression value from calls to the function template. Okay, call doThing and pass it a const expression int via doThing x, where x is the const expression int. We want to pass the doThing, like doThing 3, 3 as x. Non-type template parameters let us pass const expression values to functions because function parameters cannot be expression, or cannot be const expression. Of possibly different types, because they can still be the different types. We can call doThing with two different data type, or with two arguments of differing data types. We when a function template is called, well, hold on, and instantiate a function template when the primary, well, a function template is called a set of arguments. The compiler creates a version of the function with template parameters of the type that match the arguments. The calls arguments. If the arguments match the primary function template. Instantiating a function template is the process by which the compiler generates a specific version of the specific template function via calls to the primary template with arguments. Well, let's see. Instantiating a function template well, let's say function template instantiation is the process by which the compiler generates a version of the template of the primary template function that with parameters that match the types of the data types of the arguments in calls to the function template. Okay. Excuse me. Isn't that it? Guess I could just do that and then I don't have to do IOStream, huh? Oops, didn't mean to debug like that. Exited with code 4 because 4 is greater. Okay. Okay. Provide a default argument for a function parameter using the assignment operator and the R value the function parameter should use as a default variable. We must ensure that the default argument is not to the left in the function signature, or left of non-default of parameters without default arguments in the function signature, because if we call the function so like if I had void do thing int x int y and y was assigned to be 10 as the default argument, I could call it with x and ignore y. But if it was x is 10 and then y and I call it with just y, yeah. If we call the function, or well, because calls to such a function would not tell the compiler whether the value, whether calls argument is initializing the parameter with the default argument or the next argument. Keep the default argument parameters to the right. That way we explicitly initialize any non-default value parameters, non-default argument parameters, and either omit the final parameters to use the default argument or initialize it as well. We can end a function signature with its delete. Wait, actually, hold on. Oh wait, yeah, because we don't use it, we just delete it. So, well, what if we had... We get two issues. We get an issue here. I mean, I guess, do we just comment this out? And that's fine. So what if I had... Oh, we just need the signature. So the declaration needs to end... Excuse me, with a with equals delete semicolon. So we have... Like this, yep. Well, hold on. Excuse me. Disallow calls to it. Well, I think that's fine actually. Because if we have a definition and then we delete it, is this fine? Excuse me. Yeah, it's fine. Okay, so if it's in a different file, then it's okay. Otherwise, it's replacing this with the body. So that alone suffices. If we end the declaration with when the body is defined in another file. If the body is defined in the same file, the compiler will error saying the function already has a body because the okay. Okay. If a function call is ambiguous between multiple overloads, the compiler will fail and error. Ambiguous call is caused by performing an implicit conversion of the argument to the parameters of the overloads when the conversion makes more than one function call or one overload. The call match more than or call make more than one overload, make multiple overloads equally viable, building ambiguity. If a function call is ambiguous between multiple overloads, the compiler will fail and error. The ambiguous call will yield an error. The ambiguous call is caused by the compiler performing an implicit conversion of the arguments to the parameters in the overloads when the conversion makes multiple overloads equally viable, building ambiguity about which to call. The compiler uses parameter types and counts to distinguish between overloads. Okay. Function overloading is when we can create multiple versions, multiple functions with a shared identifier to handle different data types and counts within call, or different data types and counts for call arguments to have the same identifier call different functions depending on what arguments we pass. Is when we create multiple versions of a function with multiple functions with a shared identifier but different parameter types and or counts that the compiler determines which function to call by matching the call arguments to the best matching function. Function overload. This lets us use one identifier call to get different behavior that fits our arguments. i.e., we can call add to 3 to add 2 and 3, and add 2.2 or 2.3, 5.3 to add 2.3 and 5.3. Doubles instead of, well, we can call add, sure, int float, or well, an int for add float with add 1, 2, or add 1.0, 2.0 to perform integer or floating point division without needing functions with separate names. 10.9 type deduction for functions. Auto can be used in a function declaration to make the return value's data type match the data type of the value being returned. i.e., if the function signature includes an auto return type, but the function returns a standard string, then the function will return a standard string. After compilation, well, I don't know if it would change necessarily. Auto would deduce that the function returns a standard string. Excuse me. Auto may also be used to create abbreviated function templates by substituting placeholder arguments with auto. Placeholder parameter types with auto. And C++20 context. Auto is a type name, as a data type, performs makes the compiler perform type deduction, setting the type of the object to be the type of the initializer. If the value is a complex type, lots of syntax, auto can be a shortcut especially if we don't care what the data type is. Okay. Two ways, via using or type def. Using ulong unsigned long, type def unsigned long ulong. Cool. You can explicitly convert a double to an int using casts, specifically static casts, i.e. static cast to an int 3.0 converts the double 3.0 to an integer 3. This prevents the compiler. Oh yeah, sure, that's fine. Arithmetic. Don't these occur when generating or when determining a common type or an arithmetic conversion? Hold on. Conversions occur when using arithmetic operators with operands of different data types, i.e. 3.0 plus 3. 3.0 is a double, or well, left operand is a double and right operand is an int. There are usual arithmetic conversion rules where, depending on the data types, a common type will be determined. So the expression will yield that type. In this case, double. Nearing conversions occur when converting data of one type to another when the final data type cannot represent all values of the initial data type. Nearing conversions may result in data loss depending on the specific value converted. List initialization will make the compiler. Is it just a warning? Narrowing conversions occur when converting data of one type to another when the final data type cannot represent all values of the initial data type. Narrowing conversions may result in data loss depending on the specific value converted. List initialization will make the compiler error when initializing an object with a value that yields an implicit narrowing conversion. Assigning a double value to an int variable yield a narrowing conversion. List initialization will make the compiler detect an error upon seeing this. The compiler error upon detecting this. If we don't use list initialization, the decimal is dropped. So 27.5 will become 27. Numeric promotion is when an integral or floating point value is converted to a wider memory data type that matches the architecture's preferred with version, or preferred with data type. i.e., if we initialize an integer value with a short, or an integer variable with a short variable's value, the short value will be implicitly numerically promoted to being an integer, the wider data type that matches the architecture's or implementation's preferred integer type, then will be assigned to the integer value or variable. Same for float being assigned to a double variable. Same for arithmetic conversions between ints and shorts and floats and doubles. 10.1. Since the common type will be an integer and a double, so the short and float will be numerically promoted to the preferred wider types. Implicit type conversion is when initialize a variable of one type with data of another type, or return data of one type as another type, i.e. returning a float value as an int, or vice versa, or initializing a short int with a bool value. .6. Assert executes or evaluates its condition at runtime. Static assert evaluates its condition at compile time. Excuse me. And thus requires a const expression condition to be executable for it to execute at compile time. can check, we can evaluate the standard character input condition or standard character input dot fail. Or is it fail? Or is it error? It is fail, okay. How can we detect and handle errors in your program? We can detect errors by validating and challenging assumptions with edge case data, or with data of different types and values. We can create unit tests to call units of code with different values and use asserts to abort the program if conditions evaluate to unexpected, to false when true is expected. Semantic errors are not language errors, that compiler will detect. More like decrementing an unsigned loop counter in a loop, yielding an infinite loop via modulo wrapping, or calling a function at the wrong time, or forgetting to break or return from a switch case, yielding unwanted fall through. Code coverage measures the proportion of code executed in a given unit as tested by a unit test. This is the proportion of code in a given unit executed, proportion of a code that a unit, proportion of code of a unit's code that a unit test executes. The more code we test, we test code to identify errors and handle and validate input. Identify and handle errors and validate input to do the same. You can include random.h. What is that? I really love this song. Wow, she's got great eyes. Oops. The user defined random.h header with a g in it. Random an approximately random number in any file that needs one. Needs them. To generate file that needs them. Okay. After seeding a Mersenne twister using a standard seed sequence initialized with random numbers from standard random device and or standard chrono steady clock. What's the point of me including steady clock? Because random number already gets semi-random numbers. It seems like, does it increase the randomness? I'm not sure. Because if we, instead of steady clock, which is 1 moment at a time in an entire day, well, maybe the range of values for that is wider than the random numbers from a random device. Let's test that. And now we can also do Oh yeah, that's why. Okay, I was hoping that that's why we would include it. I could have done that better. Well, no, I can't. Well, I guess I could. No, I can't. Not on this keyboard. I can't do shift up arrow or down arrow. It's 60%. Excuse me. Excuse me. Okay. Like right now. That note in the back. Oh, you can't even hear that, but there's a note in the background, and it sounds like the notes that are used in the background of Schedule 1. Oh, I love it. I love those. That I don't know what the instrument is. What a... I'm bookmarking this thing. No, I can't because then I'm gonna get tired of it. Where in the fuck is... I don't know where this guy went. Where the end was. It disappeared. Okay. Well, we could also do standard exit, right? Oh, oops. Wait. Wait, what is it called? Is it C standard definition? Oh, C standard library. What's happening here? I think we have to do... Really? Wait, why is it saying that? Oh, oops. We're not using a semicolon. That'll do it. There's a linker issue? Oh. I still have another fucking file I haven't deleted yet. Excuse me. Oh fuck. And at 47, I think. Oh, nice. Yeah, this is very nice. It's still generating. Holy shit. Okay. L values are named identified objects. Okay. I'm gonna read the improvements. Not all function return values are R value. I'll read the improvements over the next days and see if this is the best part, the best way. Not all return value, like, yeah, if I'm running and someone's like, yeah, you're running really well, bro. I mean, maybe that validates something internally and I was worried about something being an issue and it's not, but I'd rather someone point out the stuff. Because if they're not pointing it out, then maybe it's fine. Therefore, that not all return values are return values. Yeah, because if we return reference, we're returning a variable, or like where it's located in memory, then that's going to evaluate to the variable, which is an L value. Makes sense. Wow, this version of the AI is more respectful. Holy shit, he's not saying you're rambling, retard, rambling, do better, stupid. L values can be converted in R value context via implicit conversions, but not all R values can become L values. R values can become L values. Noted. Okay. L values have an address, can be taken with and R values generally do not. Okay. The address. Here comes the alarm. I can hear it. I can smell it. 3, 2, 1. Never mind. Correct that compound data types are made from fundamental types. Or, okay, ignore that. Functions are not typically... Wait, did I not? Oh, I think I did 8. I think it's the next minute. Oh my god, I debated myself. Function... Oh, there's the note. Oh, so good. I gotta play that for a second. Not yet. It's gonna do it in a sec. Maybe it's not. That little... It'll do it again in a second. Okay, it might not.